All right. Okay, so we were studying a theorem called Green's theorem. And what Green's theorem said, so Green's theorem is really important. And what Green's theorem says is the following, just to remind you. If I have a region in the xy plane, say with some boundary curve C oriented positively, and I have the interior, which is an interior region D, what Green's theorem said was that and also I've got some vector field F, which is P and Q, that the integral around the boundary C of P dx plus Q dy was equal to the double integral of the Q dx minus dP dy dA over the region D. So Green's theorem is basically telling you, from what we talked about last time, that the circulation of the vector field around the boundary is equal to the sum of all the little rotations in the interior. That is what Green's theorem says. So this is a theorem of two dimensions. So I would like to come up with a way to think about this theorem in 3 dimensions. And so one way to do that would be, what if I just took the theorem and I put it in 3 dimensions? I mean, I could take a 2-dimensional region and pretend it's in 3D just by letting z be 0. So I could take this region and I could put it in 3D instead, sort of just by tipping it over. Now there's my boundary curve C. It's still filled in with a flat, sort of a flat area. Now we're in the x, y, and z planes. It's still true that the circulation in the interior of that flat set, the rotation in the interior is equal to circulation in the boundary because this is still a 2-dimensional setting. Still 2D. Green's theorem still applies. But what we can do instead is we had that alternate formulation of Green's theorem that involved the dot product, so we could put the curl in. So if you imagine that you attach to this surface at every point the unit vector k, the idea is that these guys are normal vectors. They're perpendicular to the surface, right? So there's all these little k's sticking out, the unit vector that's perpendicular to the z-axis. And in this picture, with that notational trick that I showed you yesterday, I can write the other restatement of Green's theorem that's exactly the same, which is that this is the integral around C of the vector field F dot dr, that's just circulation around the curve C, was equal to the double integral over D of the curl of F dotted with the K vector dA. Those were 2 different versions of the same theorem, but this is nothing but a notational shift. So I think last time I pointed out that this del cross F, if you actually calculate that for the vector field F is equal to PQ0, what comes out of del cross F is dq, this is 0, 0, dq dx minus dp dy. So I've done nothing here except a notational shift. But notice, by thinking of this in 3 dimensions, I've got something that I have a hope maybe I can take this theorem and apply it to more interesting shapes than this one. So one way of thinking about what I'm going to do here is the following. I have this curve sitting in 3-dimensional space. It's filled in with this flat sheet. There's normal vectors attached to it everywhere. And what Green's theorem is saying, the rotation around those normal vectors adds up to the circulation around the boundary. If I got a fan, or I imagine that this was like a rubber sheet, and I blew into it from the bottom, it would expand into something 3-dimensional. So you can imagine the boundary curve would stay the boundary curve. And then you could take that sheet and you could sort of puff it up. So you can imagine, maybe I can do something like this. Single dot here. So you get some figure like this. So the idea is you're supposed to think of this figure as being like a puffed up version of this one, right? I've sort of taken this as like a rubber sheet or like bubble gum or something, and I've blown into it and expanded it into something that looks like this. So this is a surface. So I've taken a flat thing and I've blown it up into something that's not flat. But notice, I didn't change the boundary. The boundary's the same. I think about that pink ring there as remaining the pink ring. It didn't do anything. I've blown into that rubber sheet from the bottom and belted up into a surface. This is a surface that is not a function. It's not a graph. The reason it's not a graph is because it fails the vertical line test, right? So this is a surface that I cannot write down as z is equal to f of x and y. And yet, if I imagined that I started with this flat sheet that had all of these normal vectors attached to it, and I kept track of what happened to the normal vectors as I blew this thing up, you would end up with something that looked like this. That would be a normal vector, that would be a normal vector. These vectors still stay perpendicular to the surface, because if you imagine that you did this in a nice, it would be disgusting, but if you have bubble gum with a bunch of hair stuck to it, and you blew it up, the idea is that the hair, instead of pointing straight up, it would sort of like, it would move with the bubble, right? I didn't use that analogy in the first class. It just occurred to me. Okay, so the idea here is Green's theorem basically still works in this setting. If I took the surface and I broke it up into a bunch of little tangent planes, and I calculated the circulation of the vector field through the surface around each one of those little planes, Green's theorem would apply in this box, and it would apply in this box, and it would apply in this box. Green's theorem works on all those. The curl of the vector field around that vector, if I add them all up, I still get circulation around the boundary. So I'm going to give you a preview of what we want to prove. My claim is that basically is just Green's theorem, but puffed up. So the 3D version of Green's theorem is called Stokes' theorem. And Stokes' theorem says the integral around C of f dot dr, the circulation around the boundary, is equal to the double integral on the surface of the curl of f dotted with a normal vector dA. That's the same theorem as Green's theorem. It says the circulation, or the curl, the rotation of the vector field through the surface, if I add up all these little tendencies to rotate in the surface, I still get the circulation around the boundary. The problem is, I don't know how to write down the surface S. It's not a graph, so I can't write z is equal to f of x and y. And I don't know what this dot n dA thing even means, because here, this was a double integral I could solve just using flat two-dimensional methods. Oh, it's a region between two curves, then integrate from x equals a to x equals b. Now, I don't know how to chop the surface up into little bits and integrate over it. That's hard. That picture says, take the green region and chop it up into rectangles and add up what happens on the rectangles. Now I'm telling you, take the surface and cut it up into little parallelograms and then glue them together like armadillo scales. And if I add up all of that math, then I get the circulation around the boundary. These things are not yet well defined. So our goal here is to describe S in some way to make this make sense. So I want this to be a sensible statement that I can work on mathematically. How do I describe a surface that does not look like z is equal to f of x and y? What does this dot, the normal vector, times dA even mean in this context? This is going to somehow have to correspond to the area of these guys in order for this to make sense. I don't know how to calculate surface area. So what we're going to do in 16.5 and 16.6 is we're going to talk about how to make this stuff, 16.6 and 16.7 is how to make this part of the picture make sense so that in 16.8 we can do this theorem. Okay, so what is 16.6 say? So 16.6 is about what are called parametrized surfaces. So parametrized surfaces are related to parametrized curves. So remember, a parametrized curve is a function, R. And what R does is it eats an interval, say A to B, and then spits out some three-dimensional points, right? So it maps into R3, so it's got three outputs. And the way we think about parametrized curves is eat one input, produce three outputs. So for example, we've dealt with R of t is equal to cosine of t, sine of t, t. That was the helix, or the helicoid spiral. Say I let t go from 0 to 2 pi. Then what the helicoid spiral does, in this case, is it takes an interval starting at 0 and ending at 2 pi, and it turns it into sort of a twisty thing that goes around like this. One rotation of the spiral from 0 to 2 pi. So it's taken, the map has taken a one-dimensional, simple, straight, flat interval and has turned it into a three-dimensional, twisty thing. It's curved it in three-dimensional space. It's still one-dimensional because it ate an interval and produced a curve, but the curve can curl and twist. And then we had all kinds of formulas for working with this that involved the length of R and the derivative of R. There were, so like the length formula had the length of the derivative inside of it. So what we want to do is the same sort of thing, but where I want to create not just a one-dimensional looking output, but a two-dimensional looking output instead. So a parametrized surface is a function. The book uses the letter R for this as well, so I'm not going to use that because I'm trying to distinguish between curves and surfaces. So a typical letter here that's used is capital Phi, and it's a function of two variables, u and v. So two parameters. Phi eats a region D in R2. That just means a two-dimensional region, and it spits out something in R3. So capital Phi of u and v is a map that produces an x of u and v, a y of u and v, and a z of u and v. So it eats two parameters and produces a three-dimensional thing. And the idea here is what makes this curve one-dimensional is I can move forward or backwards along the interval, and it corresponds to a little forward or backward motion on the curve. Curves are one-dimensional because you can move forward or backwards on them. Yes, you're in three-dimensional space, but you lived in the curve. At any point, you can go forwards or backwards. In a surface in R3 is two-dimensional because you can move in two directions. The general picture here would look something like this. I start with some area inside of the UV plane, and I hit it with a map Phi, and what comes out might be some kind of weird looking blob or paraboloid or anything, right? A flat rectangle in two dimensions goes in, and some sort of figure in R3 comes out, a surface. Surface here is like a thin two-dimensional bent distortion of a piece of paper, for example. So this is 2D, and this is 3D. And the fact that the idea is just like a parametrized curve can bend and distort an interval into a twisty thing in 3D, a parametrized surface can take a flat rectangle and bend and curve it into something like a paraboloid or a sphere or anything else. right, so let me give you some examples of how this works. Okay, so here's example 1. I give you phi of u and v is equal to u plus v, v, v. Say where u runs from 0 to 1 and v runs from 0 to 1. So in the UV plane, we have this square. This is in the UV plane. And then phi looks at this square, it eats it, and produces a surface. Now, normally, when you're given a parametrized surface, you don't have to find the parameterization. They're just standard things, and they're given to you. It's worth thinking through what phi actually does here, since this is the first time we're looking at this. So this is going to do something in 3 dimensions. One easy way of keeping track of what's happening is just plug in some points and hope we can understand. So in order to start doing that, I might start writing down some points. What is phi of 0, 0? 0, 0, 0, right? So 0, 0, 0 ended up right there. As I trace along this line segment right here, what all of those points have in common is that v is equal to 0. So that particular line segment right there corresponds to phi of u, that's a u, phi of u 0, which is u 0, 0. That point starts when u is equal to 0 at the point 0, 0, 0, and it ends when u is equal to 1 at the point 1, 0, 0. So as I travel that green line, I run from 0, 0, 0 to 1, 0, 0. So that green line corresponds to that little piece of the x-axis in R3. Likewise, if I was on this line segment, that corresponds to points on which the u value is equal to 0. Phi of 0v is equal to v, v, v. That one starts at 0, 0, 0 and ends at 1, 1, 1. Let's see if I can draw 1, 1, 1. So 1, 1, 1 would be something like 1, 1, 1. That's like an arrow coming out the board at you like this. I know it's hard to see. 1, 1, 1. Okay, so that line segment got turned into something that looks like this. I might as well keep track of what happened up here. That's the point 1, 1 in the UV plane. Phi of 1, 1 turns into the vector 2, 1, 1. 2, 1, 1. 2 units out, 1 unit over, 1 unit up. 2, 1, 1 is like, I gotta get higher than that. 2 is gonna be out here. All right, now I have drawn this basically an impossible to understand way, which I apologize for. This point connects to there. I really fixed what I was trying to draw. You have this point, which is the purple point. You come down to this point, which is the green point. You come out the board at you to a point up here, which is going to be this yellow point right here. And then you travel parallel to that to a point right here, which is the blue point. That's this edge and this one. So let's see if I can model what I'm doing here. So these vectors right here, the green and the yellow one, the green vector points this way and the yellow one's supposed to point up like this. So there's a vector here and a vector here. So what have I drawn? It's a piece of a plane. It's a piece of a plane. It's taken this rectangle and sort of turn it up in 3 dimensions. So yeah, this is a parametrized plane. So this is a parametrized plane. And it's not the whole plane, it's just the piece of it that corresponds to u going between 0, 1 and v going between 0, 1. So it took that rectangle and it turned it up. And more generally, you can make any plane like this into a parametric function with a sort of standard construction. If you write the map phi of u and v is equal to an initial point x naught, y naught, z naught, plus u times some kind of first vector plus v times some sort of second vector. Anything that you write down with that description will be a plane. That's sort of your anchor point. This says there's one direction you can travel scaling by u and another direction you can travel scaling by v. So this is the general form of a parametrized plane. General form of a plane. All right, let's get an example that may be a little bit easier. This one I'll just give you. Phi of u of v is equal to, let's see, cosine u sine v, sine u, sine v, cosine v, where u goes from 0 to 2 pi and v goes from 0 to pi. So that map eats a rectangle in the UV plane. It goes from 0 to 2 pi and 0 to pi. There's the rectangle it eats right there. And turns it into a radius. So there is no rho in here, which means the rho is equal to 1. But these are spherical coordinates. So this is a way to turn a sphere, sort of a notoriously hard thing to write. You got square roots and plus and minus parts or whatever. This map, phi, will eat that orange rectangle and turn it into a sphere. That's how. This is one way to parameterize spheres. So notice, the nice thing about this is I've taken something that in Euclidean or Cartesian coordinates is very difficult to work with, and I've made it essentially into the graph of a function. I've cheated. I've made the sphere into the graph of this map. And the fact that I did that is only possible essentially because the sphere is two-dimensional, so I could turn a two-dimensional thing into the sphere. Okay, the last one we'll talk about is the last example of parametrized surfaces that you should see. It's something like this. Here's example 3. If I gave you phi of u and v is equal to u, v, u squared plus v squared, say where u is between 1 and minus 1, and v is between 1 and minus 1. What am I looking at? What do you think? Paraboloid? Any other opinions? I know it's like, yeah, I can see like daylight savings. So if you were to eliminate the parameter on this one, remember eliminating the parameter works in 2 dimensions as well. If this is x and this is y and this is z, then this would say x is equal to u, y is equal to v, and z is equal to u squared plus v squared. But I could eliminate the parameter on this last equation just by substitution, and that would turn into z is equal to x squared plus y squared. It's a paraboloid. And this is generally the way that we parameterize functions. If I have a graph, z is equal to f of x and y, I could write the independent variables as x and y, and the dependent variable as z. This particular one is sort of interesting because if you actually plotted this, because it's the image of a parabola sitting over a square. So you can imagine if you had a square down here, the things that are farthest away from the origin are the corners. And the things that are closest to the origin are the edge, are the middle of the squares. And so you get this sort of paraboloid where on the edges, it kind of has this sort of tented look. And the paraboloid kind of comes down to the origin like this. Draw like this circle that happens here. Like this. So like a tented thing. Okay, so the general idea here is if z is equal to f of x and y, you can always parameterize that as phi of u and v is equal to u, v, f of u and v. All right, so the big picture with parameterized surfaces is this gets us a way of thinking about 3D surfaces as the images of 2D things. And if you were paying attention to the Green's theorem part, this would say maybe what Stokes' theorem is saying is Stokes' theorem applies to this region. Maybe we can push it through to apply to the three-dimensional region with this map. If Green's theorem works here, maybe I can 3Dize Green's theorem by pushing it through a parameterized surface. So if we're going to do that, like every good idea in calculus, what's the first thing you do when you learn a new idea in calculus? Every single time you've ever learned a new idea in calculus, the very first thing you do, you take a specific limit, which is you take the tangent plane, right? Every time you learn something new, you calculate tangent lines for it, or tangent planes. We're going to do this. We're going to do, yet again, another incredibly sophisticated way of looking at things, and we're going to immediately calculate tangent planes with it. Because that's what you do when you do calculus, is you take tangent planes. Okay, so I want to talk specifically about the example I'm going to anchor all this with is the paraboloid. I'm not going to use the restricted version on the square. I'm just going to think about the paraboloid that I have if I wrote down phi of u and v is equal to u, v, u squared plus v squared. And I'm just going to think about that as taking the uv plane and spitting out the paraboloid that looks like this. Okay, so the first thing I'm going to need is some notion of derivatives. So I'm going to make a definition. The tangent vectors of phi are, this is slightly different from the book's notation as well. I'm trying to emphasize that these are tangent vectors. The tangent vector in the u direction is the u derivative of the map phi, which is the u derivative of x, y, z, x of u and v, y of u and v, z of u and v, which is xu, yu, zu. That is the tangent in the u direction. The tangent in the v direction is the v derivative of the map v, which is x with respect to v, y with respect to v, z with respect to v. So these are just definitions. I'm defining the tangent in the u direction and the tangent in the v direction. Now, what they do is that if I had some sort of domain over here that had created this paraboloid, so you can imagine this paraboloid is maybe the effect of something like, in fact, that particular paraboloid would be the image of this, if I drew a circle here. That set turns into the parabola that I've drawn there. What this is saying is, in fact, do I want to do it that way? Yeah. What that's saying is that if I calculated a line here, and I crossed it with a line here, and I think about the point where those guys intersect with each other, which would be right here. If I took this map and I pulled it over onto this surface, I would have, let's see, so if u is equal to constant, then v is growing. So I think I get a curve that looks like this, and a curve that looks like this, and where they cross each other is at that purple point right here. The idea is the map takes lines and it turns them into lines. The maps in the original UV plane, the lines over here, get turned into curves on the surfaces over here. And the idea is that if you calculate these vectors tu and tv, that's like saying, hey, over here, I know what the tangent vector to that curve looks like because it's in flat R2 and the tangent vector is just go that way. What that turns into in the 3D picture, though, is an actual tangent vector to the plane, or to the surface. This is tangent to the surface. Tu is a vector that is tangent to the orange curve, but that also means since the orange curve is in the surface, it's tangent to the surface. And likewise, if I had a tangent vector over here, well, that's pretty easy to compute. Go up. But if you run through what that does on the surface side, you end up with TV, the tangent vector in the v direction. Those vectors correspond to vectors that are perpendicular to the surface on this side. Now, two vectors have an interesting property, which is if they're not parallel, they form a plane. In fact, since these are both tangent vectors, they sit in the tangent plane to the surface. TV and TU sit inside of a tangent plane. Well, that's pretty nice. Tangent planes are good for local approximations. That's awesome. Ultimately, what we're going to do is this Green's theorem thing, but in 3D, so we need a little bit more than that. It sure would be great if I could come up with a way to figure out a normal vector to that surface. So I had a normal vector. If I had a normal vector sticking out for this, say like I have some vector n poking out, I could describe the tangent plane just with the normal vector. Or I could calculate a flux calculation by thinking about the amount of vector field passing through the surface. Okay?
Tu cross TV.
Ah, yes indeed. Because Tu and TV are in the tangent plane, any two vectors in the tangent plane, if I crossed them, would get me a normal vector. So n, so I guess what you would say here is Tu cross TV is normal to the surface. Which is to say perpendicular. All right, so what I want to do is I actually want to plot, or I want to calculate this for the particular map that we've drawn here. And I'm going to point something out. Okay. So phi of u and v is equal to u, v, u squared plus v squared. We can just suppose that we're sitting over the top of a big enough rectangle to include the part that I'm interested in. So maybe this is minus 2, 2, 2, and minus 2. That's going to end up creating a parabola over here, sort of that has that tented shape from before. But I don't really care about the tented shape because I'm going to be working below it. So, first question is, that point right there, which is the point 1, 1. On the parabola here, I'll do this. Here's x. Here's y. There's the z-axis. Paraboloid sits over the top of it. Where does 1, 1 go in this map? 1, 1, 2. Okay, so 1, 1, 2. So that point in the UV plane got carried over to the point 1, 1, 2 on the surface. What is TU in this problem? TU is equal to 1, 0, 2u. So it's the u derivative of the map phi, right? So that is a function for tangent vectors. What is TU at the point 1, 1? I'm going to turn information in 2 dimensions into information about 3. It's the vector 1, 0, 2. What that says is that a little bit of change in the u direction over here corresponds to, let's see, what's the change in this direction? 1 means you come out this way. All right, from this point, you go out 1, and then nothing in the y direction, and up 2. So it's sort of coming up like this. that make sense? This is the vector 1, 0, 2, emanating from the point 1, 1, 2. The way to think about this is this vector is coming, I'm drawing, these are my sort of auxiliary vectors. That's out at you, and that's up 2 units. And so this vector kind of points up out at you like this, up out of the board. How about TV? TV is 0, 1, 2v. So the tangent in the v direction is going to be at the point 1, 1. Will be equal to 0, 1, 2. So if you go up here and you plot that one, that says if you went a little bit in the v direction here, that corresponds to going 1 unit in the y direction, no units in the x direction, and 2 units up, which means you would point this way. Away from the paraboloid, but up. I'm going to try to draw, I'm going to wave the yardsticks around in a second. So this is the vector 0, 1, 2. So the way I want you to think about this is the paraboloid is sort of belling out of the board at you in the first quadrant, so it sort of curves up like this. And these two vectors essentially look like this. The point that they're attached to is right here, and they're tipped out at you, and they're not at right angles to each other. They're both positive, but they sit like this. Okay? And the plane that they sit in is the tangent plane. As you move the point around the edge, the tangent, those two vectors are going to go with it, is the idea. On any circle, they look like this. As it goes up the face of the surface, what those vectors will do is they'll narrow, but they'll tip in as well. So they look like this. They still form a plane, but the angle of that plane is going to change. Down here at the bottom, those vectors look like this. So wider, but a plane that's flatter, and as they come up, they sort of do this. So now, if I actually want to define the tangent plane containing those things, I could try to calculate the normal vector. So we should expect that there's two normal vectors to these things. There's a normal vector that points out in this direction back behind them, and there's a normal vector that points out this way to the front. So if I want to calculate a normal vector in this picture, I might just say, well, my normal vector n is going to be equal to the cross product of I, j, and k, and then I'll use tu, so 1, 0, 2, and tv, which is 0, 1, and 2. And I think if you calculate this cross product, you get minus 2, 1. Zero times 2 minus 1 times 2 is negative 2. 1 times 2 is 2 minus 0, but then you put the negative for the j. And then k would be 1 times 1 minus 0 times 0, which is 1. So that says that, at least in this picture, the normal vector points back into the parabola, is the idea. So that says I'll have my two tangent vectors, and the normal vector is pointing back this direction, back into the parabola. Because it's negative in the x direction, negative in the y direction, and positive in the z. And geometrically, that makes sense to me. That if I went backwards in this direction, and backwards in this direction, and up, I would get something that looked like a normal vector pointing back into the plane. In a tipped picture, to make it more clear what I'm doing here, I'm basically saying if I rotated this picture on its side, I have a vector and a vector that looks like this, and then the normal vector n pokes out like that. So just take that image and sort of rotate it around so it looks like this. Now there's one more vitally important piece of information here, which is the whole point of all of this was not just to discover tangent planes and normal vectors. It was what I really wanted to know when I wrote down that formulation of Stokes' theorem. There was that bit at the end that looked like n times dA, some kind of unit vector looking thing in there. I need some way to chop the surface up into things that I know the area of. So my question is, if I took the rectangle formed by those two vectors and I carried it over here, what shape would it become? Not a rectangle necessarily. I start with this little flat thing formed by two vectors. And I carry it over to these two vectors. What sort of natural shape do two vectors make? Well, okay, but the whole square instead of the triangle between them gives you a parallelogram, right? Squares turn into parallelograms. How do you find the area of a parallelogram? It's cross product. So the cross product of these two vectors, then the magnitude of that cross product will be the area of that parallelogram. This is going to be the way that we set up a general notion of surface area, which is the next chapter to discuss. So all of this machinery gives us the best way to compute surface area. And that's why we haven't done any surface area so far. So I know this is a lot, and hopefully we'll just get your brains used to it by the time we see it again in the surface area chapter. So tomorrow we'll do surface area, and once we have surface area, we can actually state Stokes' theorem. Hey, see you guys.